Hey guys, today I'm building a brushless ESC completely from scratch using nothing but an STM32, a couple discrete components, and a Bootstrap setup. So this is part 1, and I just want the motor to spin reliably with an open loop 6-step commutation pattern. In part 2, I'll be adding back EMF sensing and get both boards to connect into one. So this is all based around an STM32. I'm using the board that I made in the previous video and another board that I made for this video specifically, with 3 pairs of high side and low side MOSFETs. So the way it works is there's a high side MOSFET that's connected in the middle with a phase to a low side MOSFET. And so you see this is phase A, phase B, and phase C. In the middle of each phase is connected to one of the motor phases. So the top side is connected to the microcontroller as well as the low side. And depending on which high side or low side MOSFET we turn on, it will regulate the direction of current flow and thus the direction that the motor will spin. So this is a Bootstrap setup. This is key to making our board work because the microcontroller, the STM32, can't supply more than 3.3 volts, but the supply voltage is 12 volts. And we'll be asking, can't you just put 3.3 volts into the gate of the power MOSFET? And unfortunately, to make a MOSFET turn on, it has to have a sufficient gate to source voltage. And because the motor is basically a big resistor, the source of the MOSFET is going to be 12 volts. And so 3 volts on the gate isn't enough to turn it on. It has to be sufficiently above 12 volts. And so we have a capacitor, which essentially adds the voltage on the source to the voltage on the supply. This is because capacitors preserve potential difference. So in a capacitor, if we set the potential difference at 5 volts, so ground on the bottom and 5 volts on the top, if we set the bottom of that capacitor up to 5 volts, what's going to happen is that the capacitor is going to preserve the potential difference. And so the top of the capacitor is going to rise up to 10 volts. And so the reason we do this in a Bootstrap circuit is so that we can set the gate of the MOSFET higher than the actual supply voltage. And when we do this, we can control the power MOSFET even though our microcontroller doesn't supply more than 3.3 volts. So this is a quick simulation so you can see how it works. When the control MOSFET is pulled down to ground, the capacitor recharges, and when it's set back up high, the capacitor can discharge into the gate with its high voltage, turning the high side on. So this is it on the board, and you can see it's not that big. We're using SS14 Schottky diodes because they're really quick and have a low voltage drop, and so the Bootstrap is efficient, and we can use it in a high PWM so that we don't lose too much voltage. So this is a quick diagram on how the phases are connected. So we have phase A on the left, phase B, and then phase C. So to spin the motor one way, to set one phase, we set phase A high and phase B low. And to get the other current flow, we set phase B high and phase A low. And we all do this from the Bootstrap setup. So each of the high side MOSFETs has its own Bootstrap, and the low side MOSFETs are connected directly to the STM32 through DuPont connectors. To get a brushless motor to do a full commutation, we have to do 6 steps. So that's what I'm writing out right now on the right. And essentially that's what the microcontroller is doing. It's setting phase A high, phase B low, and then it's alternating phase A high, phase C low, and then it does that over and over again to get the motor to complete one commutation. So this is going to be a quick visual diagram so that you can see exactly what the microcontroller is doing, just so you can follow along a little bit better. In each step, only 2 phases will be powered. That's because we want a magnetic angle just so that the motor can actually spin. But also, we can use the unpowered phase. So in this case, for the first part, is going to be phase A and B are powered, and the phase C is left unpowered. What we can do is we can use phase C to measure the back EMF. And what this will let us do is get the rough position of the rotor. Once we get the rotor spinning fast enough, we can control the speed precisely because we know the exact current that's being generated from the motor spinning on the unpowered phase. So to put it simply, all the microcontroller is doing is it is switching each phase, and what that does is it sets the current flowing in the stator, changing the motor angle, and if we repeat that enough times, we'll see that the motor will start spinning. What my controller does, the way we control the speed, is we can add a delay between each step. So when phase AB is on, we add a small 1 millisecond delay before switching it to phase AC. And so if we shorten that delay, the motor will start spinning faster. And eventually we can start measuring back EMF and get a high-speed, precise rotor RPM. I've left the schematic for this board in the description so that you can check it out for yourself. Maybe you can copy some of the schematic into your own project. In the next video, I'll be putting these two boards together into one. I'll be adding back EMF and support for both brushless and brushed motors. So until then, happy holidays, and I'll see you next time.